homework problems, and in one of the homework problems, in the third problem, actually, we have a 3-point moving average system, and we have an input that is a sinusoid. That is a sinusoid. And we ask if the output is also a sinusoid. So what is your answer? Is it a sinusoid as well? What kind of sinusoid is it? Is it a cosine? No, it's a sine. Okay. It's a cosine. It's a sine. Okay. And or you can say it's cosine with a phase half pi. Okay. These two are the same thing, right? And so for a 3-point moving average, we have a sinusoid input and we have a sinusoid output. So that's the moving average case. How about more general? More generally, is this true? We would like to ask this question and think about this now. And this will bring us to the frequency domain of the LTI system. Okay, why is it a frequency domain? Because when we have a sinusoid, then we only have a single tone, right? So there's only one frequency to talk about right here, this single tone here. So let's think about the simpler case, a related case, when the input is a complex exponential. Xn is a complex exponential, like so. And this is for all n. Okay, this is for all n. And let's compute the output at this time. Yn, right? Our Hn, when we write something like this, what does that mean? What kind of system is that? When we have a box and we have a function in there, what kind of system is this? It's an LTI system. It's an LTI system, and that's the impulse response, because only with an LTI system we write something like this. Because only with an LTI system the impulse response will characterize the whole system. Okay. Now let's compute the output at this point. Let's write down the convolution sum, hk, and then xn minus k. And xn minus k, we're going to put down xn minus k here, right? n minus k. And that's the convolutional sum. K goes from minus infinity to infinity, right? And what does this look like? K from minus infinity to infinity, right? So we have a k, and this k is actually a dummy variable here, right? Dummy variable here, right? And then we have something that is independent of k. With something that's independent of k, the first part here, that's independent of k, right? Ej omega 0 n, that is independent of k, so let's pull that out. We will pull that out. Ej omega 0 n, and then sum hk e minus j omega 0 k, like so. All right? So we have a complex exponential here, and we have a big summation here. We have a summation here. What does this summation depend on? What does this summation depend on? It has this k, right? And it has this omega 0, right? The summation, the total, the summation, what does it depend on? Does it, when we compute every term and we sum them up, because this is a summation, right? And there are infinitely many terms in this summation. So we add each term up what do we end up with? Does it gonna depend on k, this big summation here? What does it depend on? Omega 0. Thank you very, very much. It's gonna be a quantity that depends on omega 0 right here. So let's call this, it's gonna be a function of omega 0, right? So let's call this H-E-J omega 0, okay? This notation looks a little bit weird, right? This notation looks a little bit weird. It's a function of omega 0, but we write it in a little bit awkwardly. But we will see why we write it in this way later. Okay. So this is going to be a function of omega 0. So let's write it like this. Right? Now, we can write yn as ej omega 0 n and H-E-J omega 0, like so. Is this a complex exponential function? It's a complex exponential function, right? It's a complex exponential function. Our input is a complex exponential function with this omega 0 here. This is frequency omega 0 here. What is the frequency here? What is the frequency for this y? Okay, let me write it down. It's also in a complex exponential. Complex exponential. It's also a complex exponential, right? So what is going to be? The frequency, it has the same omega 0 as the input, right? So when we apply a complex exponential with omega 0, then at the output, we also get a complex exponential with omega 0, but now there is a extra term. What is this extra term? It's a scalar. It's a scalar, right? It's a scalar, and it's a complex scalar in general, and it depends on omega 0. Okay. So when we have a complex exponential input, our output is also complex exponential, and I think that's what you have for 3b. That's the answer you have for 3b, right? That output is also a complex exponential. All right. And when we talked about this, so when we have a complex exponential, we know easily what the output is. If we only know this is a function of omega 0. And this function, we will give it a name. This function we call H-E-J omega. We defined it as H-E-J omega as HK E minus J omega N. Let omega K goes from minus infinity to infinity. This one is what we call frequency response of the LTI system. And just now in your example 3b, problem 3b, yes, 3b, what is this number? In problem 3b, what is this number? Is it real or is it complex? Complex, it's complex, right? So in general, it's complex. It's complex. And so if it's complex number, when we represent a complex number, how do we represent it? It's complex, right? So if we have a complex number, C is equal to A plus JB, we have a complex number. Oh, well, we already have a representation, right? We express it in terms of real part and imaginary part, right? And is there another way to express a complex number? And the other way is usually more popular when we are talking about signals and systems, things like this. We can also express it in terms of polar form, right? We can express this in terms of polar form. E, J, theta. And And this theta is, so that's usually the way we express a complex number when we are talking about signals, things like this. So when we have a complex number like this, we will write it as the magnitude part and also the phase part. The phase part is of course a function of omega. So we write it like this. And now this, the magnitude part is what we call the magnitude response. And this, that look a little bit complicated, this notation is called the phase response. For example, Hn is delta n minus 1, all right? Then what would be the frequency response? Hn is this function, right? That's Hn. And by definition, here's the frequency response. In this summation, there are k goes from minus infinity to infinity, right? But for this example, how many terms are going to be there in the summation? Just one, right? Because H has only one non-zero coefficient, right? So there is one term. And so Hej omega would be only the term k equal to 1. Because Hn has a non-zero sample only at n equal to 1, right? So only 1. And that is k equal to 1. When k is equal to 1, it is E minus j omega. Is that okay? All right, so let's look at this function and let's see what the function looks like. All right, we can either look at it in terms of real part and the imaginary part, or we can look at the magnitude response and the phase response. Let's look at magnitude and phase. What would be the magnitude? The magnitude is 1, right? And it's for all omega. How about the phase? What would be the phase for this one? Omega and minus, right? Omega and a minus. Okay, so it's minus omega. Okay, so it's a minus omega. All right, now let's draw this picture. This is omega, and that's the magnitude. And it's equal to 1 for all omega. This is 0 and this is 1 for all omega, right? And then the phase part, the phase function will be, this is 0 and it's minus omega. So let's draw minus omega like this. Okay, so for example, when omega is equal to pi, this value here will be minus pi. Let's come back to here. We have Yn. Now it has Hej omega 0 and Ej omega 0 n plus the phase at omega 0. Okay. So it will be a complex exponential with this amplitude that is equal to h, the magnitude of h at omega 0. And there's an extra term which is the phase of h at omega 0. Now let's look at some properties of h. First of all, see this definition here. We have this Ej omega, right? So this function, let's try to get acquainted. Let's look at, for example, omega plus 2 pi. The value of h at omega plus 2 pi. How is it related to the value of h at omega? They are equal, right? They are equal. They are equal. Oh, what does that mean? If they are equal, what does that mean? What kind of function is h? When we have omega plus 2 pi equal to omega, then that means it is periodic. It's periodic. So it's periodic. And what is the period? Period is 2 pi. Thank you. The period is 2 pi. And when omega is equal to 0, this is a particular frequency. We call this the DC frequency. This is called the DC frequency. And omega equal to pi, this is called the, well, have you heard about the name? When omega is equal to pi? It's actually the name of a brilliant person. It's called Nyquist. Nyquist. Omega equal to pi is called the Nyquist frequency. If it's a periodic, then it means when we look at the frequency response, we only need to consider a period. For example, we only need to consider from minus pi to pi or from 0 to 2 pi. Just one period. Okay. All right, how about the magnitude response? Is it periodic? Is the magnitude response periodic as well? Periodic. Is the magnitude response periodic? It is, right? Because the h itself is a periodic, and we take the magnitude, of course, it's going to be periodic. So yes, it's periodic. How about the phase? It too, right? The phase response is also periodic. All right. So we only need to consider a period. So when we plot the magnitude response, we only need to plot, for example, from minus pi to pi. All right? We only need to plot one period. And for phase, that too, we only need to consider, for example, from minus pi to pi. From minus pi to pi. So this is pi. Or we can plot from 0 to 2 pi. Okay. If we plot from 0 to 2 pi, then we can plot it like, if it's from 0 to 2 pi, this is 2 pi, okay? And it will goes down again, right? But minus pi is the same as pi. So we can also draw it like this, okay? From 0 to 2 pi. Alrighty, now let's look at one example for this Hn. Suppose our input Xn is Ej 4 over pi n. Okay, that's what would be our output. What would be the output in this case? Can we read directly from the frequency response and phase response and determine what the output is? We have derived, we know that if it's an exponential input, then complex exponential, then Yn is equal to this thing, right? So we need to know the value of h at omega 0, magnitude, and the phase. Okay. So what would be the magnitude of h at pi over 4? The magnitude of h at pi over 4. That would be pi over 4, right here, right? So if the value is equal to 1, because it's 1 for all omega. And what would be the value of h at pi over 4? That would be right here, right? We fill in Hej omega 0 magnitude, which is equal to 1. Then Ej pi over 4 n plus the phase part, which is this thing, right? So that would be minus pi over 4. All right, and for a system like this, we have a name for it because its magnitude is 1 for all omega, so we call such a system OPAS. OPAS, because its magnitude is a constant. We will talk about OPAS a little bit later in this semester. Let's talk about the case of real HN. Okay, why do we want to talk about real HN? Real HN, that means the impulse response is real. It has a real coefficient. Okay, so why do we want to talk about real HN in particular? Because very likely our system is going to have a real coefficient, right? So, and if HN is real, that means in particular when we take the complex conjugate, we still get the same thing, right? All right. So HN is real. How does that reflect on the frequency response? Because this is a constraint, right? This is a constraint. There's a condition right here. And how does this condition reflect on the frequency response of H, Ej omega? H, Ej omega, we know is like that, right? Hk E minus j omega k. K goes from minus infinity to infinity, right? And we know if we take conjugate of H, we still get the same thing, so let's do that. Let's take a conjugate of both sides. Then we get conjugate, conjugate, and a conjugate. Okay. And when we take conjugate of H, we still get the same H. So this is actually just H. Just H, right? Okay. So this is just the H and the plus Ej omega k. Okay. And we want to know how is it related to the frequency response of H. Okay, so let's try to rewrite it a little bit. E minus j. We still want it to look like the frequency response, right? But it is the frequency response. Let's write it like this. Then how is this related to the frequency response of H? H, E, J, and how is it related to the frequency response of H? That would be the frequency response. Does that look like the frequency response of H? If we compare this one and this one, how do they differ? Minus omega, right? Minus omega. So it's actually the frequency response of H evaluated at minus omega. Okay, so what does that mean about the frequency response? What does that mean about the frequency response? That means there's certain symmetry about the frequency response. The value of H minus omega, the value of H at minus omega is the conjugate of H at omega. All right, the value at minus omega, so here we have, suppose this is omega, okay? Some omega, omega 0, let's say this is omega 0, and omega minus omega 0 will be on the other side, right? So omega, the value of H at minus omega 0 here is the value of H at omega 0 here with a conjugate. Okay. And what does that mean? For example, the value of H at minus pi over 2 is the same as the value of h at pi over 2 and then conjugate. All right? So that's the frequency response, right? That's the conjugate property that we found in the frequency response. How about the magnitude? The magnitude. When we look at the magnitude, what does this tell us about the magnitude? If we look at the magnitude at omega and at minus omega, how would they be related? They are equal. Thank you. They are equal. Why? Because the value at omega 0 and minus omega 0, they are complex conjugate of each other. So when you take the magnitude, then they are the same thing. How about phase? How are phase at omega and minus omega related? These two are complex conjugate, right? When they are complex conjugate, how about the phase? There will be an extra minus sign. Okay? So what does that say about the magnitude function? It's an even function. And the phase is an odd function. And we can come back to our example here and see if this is true here. Is this a even function? Indeed, it's true, right? It's symmetric with respect to the DC frequency. How about the phase? The phase is an odd function. Okay. Now suppose we know this is the frequency, this is the magnitude response of some filter. This is a pi, 0 to pi. This is the magnitude response, like so. And we know h is real. Do we know the whole 2 pi period? Suppose we are given a h, and we know this is what the magnitude response look like from 0 to pi. And we know h is real. H and real. Do we know the magnitude response for a 2 pi period? We do, right? What does it look like? What will it look like on the other side? It's going to be an even function, right? So it's going to look like this on the other side. Or if we want to draw from 0 to 2 pi, then that's what it would look like. Is it okay? For the same thing, if we know the phase part, we know the phase is like this. That's the phase function. And we know h is real. Can we draw the whole phase function for a 2 pi period? If we know from 0 to pi, then we should know from minus pi to 0, right? Because it's a odd function. So the other side should look like this. Okay? And here we say this function is all pass because whatever sinusoid, whatever complex exponential we apply to the system, we get, the output doesn't get attenuated at all. The amplitude of the output is not changed. It is still the same amplitude as the input, right? But here we can observe some difference, right? We can observe some difference. Let's say we have a frequency that falls here. Suppose this is our omega 0 here. Then it will get, this one is very close to 1. Say this is 1. And omega 0 is very close to 1. Then our output here, the amplitude, will be very close to 1. So it will get passed through the system. But now let's say our input frequency omega 0 is around here, where the magnitude is smaller. Then the complex exponential, the amplitude of the output complex exponential is going to be small as well. Okay, and in this case, we say it's attenuated. So if we look at a system like this, some complex exponential will get passed if the complex exponential frequency is in this range. And if the frequency of the complex exponential is around here, then it will get attenuated. The output amplitude will be smaller, sometimes much smaller than the input. So we will say then that this will be the pass band of the system and this will be the stop band. When we talked about frequency response for real system, for real impulse response, usually we only show this part from 0 to pi, because that's the only part that matters. If we know this part, we know the whole 2 pi period. So with real system, usually we only show the part from 0 to pi instead of the whole 2 pi period. 那通常我们在考虑这个 real 系统的时候呢，它的我们会考虑的大概就是我们会看的或者是说我们会秀出来的呢，大概就是只有从0到 pi 而已，因为只要知道这一部分这一半，我们就知道另外一半了。所以不管是 magnitude 啊 phase 啊或者是 frequency response 啦，我们都只要知道一个半个周期就可以了。Sometimes only 0 to pi, only 0 to pi range is shown for real HN. And suppose this is the magnitude. Okay, and we consider only the part from 0 to pi. Okay, and if the magnitude behaves like this, it's the value around this DC frequency is larger, and the value is smaller as you move towards pi, then we say this system is what kind of pass? Low pass, right? Low pass. Low pass. And if it's like this, then we say this is a high pass. And if it's like so, then we say it's band pass. Okay. And we were concerned with ourselves mostly of a real system in this class. Most of the time we will talk only about real system. Right. So now maybe we can come back to this case. We start with a complex exponential, right? As an input of an LTI system. Now let's talk about sinusoid. Sinusoid. Now suppose we have a sinusoid. Real. Still our system is real. We have a real system. And our input is a sinusoid. Our input is a sinusoid. Then what will be the output? We already know what the output will be like if the input is a complex exponential, right? But a sinusoid, we can also split it into 2 complex exponential, right? So let's do that. Xn equals the cosine, so it's actually 2 sinusoid. We can look at it as 2 sinusoid, right? And this is the output for this omega 0 n sinusoid. And if we are considering this input, what would be the output in this case? So let's say x1n is ej omega 0 n, and x2n is E minus J omega 0 n. This is an LTI system, right? So we have an input that's the sum of the 2, the average of the 2, then we can consider 2 inputs separately, right? And then we can average the output, the individual output. So this will be y1n, y1n. And what will be y2n? The output corresponding to this complex exponential will be, let me copy it down, okay? This is supposed to be minus omega 0, right? Minus omega 0. And then Ej omega 0n, and then the phase Ej minus omega 0. Okay, there's supposed to be a minus here, right? There's supposed to be a minus here, right? But we know at minus omega 0, what the magnitude would be the same as the magnitude at omega 0, right? So we have here omega 0. And at the minus omega 0, the phase will be the negative of this one here. So we would have minus, okay? And minus omega 0. All right, so that's y2. And now if we want to compute yn corresponding to this input, that will be the average of the two, right? So both terms has Ej omega 0 magnitude, so let's pull that out. And then we add these two up and divide it by 2. And what do we get? Omega 0n plus this term, and this is minus omega 0n minus this term. So the phase of this one is exactly the negative of this one here, right? So if the top one is Ej theta, this one will be E minus J theta, right? If this whole thing is Ej theta, then this will be E minus J theta. So if we add them up, we get a cosine. So we have a cosine omega 0n plus J omega 0. Well, we get 2 times cosine, but then we also have this half, so they cancel off. All right, so that's also consistent with what you have done in the homework, right? That's a 3a. In 3a, we have a cosine input, and at the output, we also have a sinusoid. We also have a sinusoid, but with the amplitude part and additional phase part, which is the phase of h at pi over 2, I think, in the homework problem. All right.